Ever wonder why eating fat keeps you energized for hours, but sugar leaves you crashing? It all comes down to what happens inside the microscopic power plant in your cells, your mitochondria. Let me show you why fat wins every time. Hey everyone, my name is Marc Bates. I'm a metabolic health coach, and this is part of my question and answer series. Your cell's secret energy factory. Why fat fuels you better than sugar. Okay, let's go to the question that started this. You've explained the efficiency difference beautifully, but I'm curious about something specific. When you say 8 acetyl-CoA molecules from palmitate versus 2 acetyl-CoA molecules from glucose, what exactly is happening in that citric acid cycle itself? If I'm a beginner trying to visualize this cycle, how would you walk me through what's actually occurring in those 8 steps? Well, it's a great question because if you didn't take any cellular biology courses, you may not have broken down what actually happens in this TCA Krebs cycle. Okay, so the TCA or citric acid cycle, right, also known as the Krebs cycle, right, is the central hub of energy metabolism inside your mitochondria. If you're new to this, think of the cycle as a metabolic Ferris wheel. Each turn of the wheel processes one molecule of acetyl-CoA, and in doing so, it strips away electrons to send to the electron transport chain where most of your ATP is made. Alright? So, just real quickly, right? There are basically two food sources that make up the citric acid cycle. One is glucose, which is the primary fuel from carbohydrates, and the other are fatty acids, which are abundant fuel from the fats that you eat. Okay? And your cells can balance between the two, right? Because either one can work, but there are differences in what they produce ultimately, and why one is a primary fuel source for the human body and the other isn't. Okay? So, but the main thing here is you're looking at each turn of the cycle produces an acetyl-CoA. So let's look at the cycle. So here we go. So there are 8 steps in the cycle, right? You start with an acetyl-CoA that started before you actually hit the TCA cycle, right? And now that's where either the fatty acid was converted into acetyl-CoA or the glucose had to go through multiple steps to produce an acetyl-CoA. Both of them produce acetyl-CoA. So the first step is your acetyl-CoA, which is a 2-carbon molecule, plus an oxyl acetate, which is a 4-carbon molecule, combined to create citrate here, right? Which is step 1, right? And that's a 6-COM. So what happens is the 2-carbon acetyl group joins a 4-carbon molecule to form a 6-carbon molecule. This is the start of the cycle. Okay, the next step is the citrate here. The citrate gets converted into isocitrate, which is also a 6-carbon. So this is just really like, it's rearranging a little bit to make it easier to do the rest of the work here. Okay, nothing real big. This is a preparation step. Okay, next step. Look down a little bit further. You get the isocrate gets turned into alpha ketoglutarate, which is a 5-carbon. Now here's what happened. One of the carbons gets chopped off, and a NAD plus is reduced to an NADH, right? So this is the first carbon loss, and this is the first time we actually are creating some energy. Okay, next group. So this alpha ketoglutarate, which is at the end of number 3, we're in step number 4. Another CO2 is chopped off, and this is why you breathe out CO2 as part of respiration, okay? And then another NAD plus becomes an NADH. So, but this has a lot of energies being developed at this point, okay? So let's keep moving on here. Step 5, that's where this succinyl-CoA right, which came out of step 4, right, turns into a succinate, which is a 4 carbon. So once again, we're losing another carbon, and a GTP becomes an ATP, which means some energy is made right here. Okay, this is one of the first steps where you get some energy. Okay, next, the succinate is processed, and it turns into an FAD, which is a coenzyme of NAD plus, grabs the electrons and becomes an FADH2. See, the H2 is hydrogen atoms, so that's the uh, electrons coming off of it, right? This powers the electron chain too, but it's a bit less efficient than NADH, but this is a necessary step to move on to the next item. This is step 7. This is where the fumarate, which was the byproduct of step 6, right, gets rearranged a little bit and turns into malate, okay, which is a 4 carbon molecule, right? That's step 7. And then we go to step 8, where the malate, which is a 4 carbon, right, one last NAD plus gets converted into an NADH, right, and the oxyl acetate is regenerated, right, to restart the cycle, and it waits for the next acetyl-CoA to come in, and bing, it just does that whole circle again. And it does this millions and billions of times every minute in your cells, and there are thousands of millions of mitochondria in each cell, potentially, that are doing in your cells, doing all this stuff, right? Because you have a couple trillion cells, 2 or 3 trillion cells in your body. Each cell is going to have thousands, if not more, mitochondria. So this is just a gigantic rapid cycle. But you can see this is where all your energy is coming from. This is a very chemical process. It's very predictable, and it's very easy to work with. And you can see why, if the fuel is wrong and you're clogging up this cycle, your energy's getting clogged up, right? And so the food that you're eating is both a fuel and a signaling device to your body on what to do with it. And if the fuel is dirty, or the fuel is the wrong type of fuel, you don't get nearly as much energy out of it. And that's the whole thing. So if you're not feeling like you're energized, or your body's showing signs that you're not getting all the energy out of your food, right? There's things we can do. Let's get to the bottom line here. Each molecule of glucose produces 36 ATP. We're going to use a palmitate, which is a 16 carbon fatty acid. It's a very common one. There are some, 14, 16, 18. Those all produce different ones, but we'll just use this one that's kind of in the middle. It produces 129 molecules of ATP. So you can see they both use the same amount of oxygen. The fatty acids produce a lot more ATP, right? And they're a lot cleaner than glucose. This is why fat is your preferred fuel, okay? So real quick, think of that circle I was showing you when I was walking through. Each step is basically a racetrack. Each lap in the cycle is for one acetyl-CoA that's fed into it. You pay your energy total at different stations along the lap. That's where an NAD plus becomes an NADH, an FAD plus becomes an NADH2, and so on. And what you get out of it is ATP. ATP is your energy. The goal here is to extract as much energy-rich currency, right, as possible to cash in at the electron transport chain for ATP. Right? So citric acid cycle is where acetyl-CoA is burned in a controlled, stepwise way. It doesn't make much ATP directly. Its job is to load up NADH and FADH2 to fuel the electron transport chain, which makes the real bulk of your ATP. Fat gives you more acetyl-CoA, more laps around the cycle, and more energy, which is why fat is the preferred fuel source. All right. Thanks for watching. Hope that wasn't a little too technical for some of you. If you have any questions, leave them in the comments. Obviously, if you want to know more, let me know. If there's anything you're missing here on how these steps work, let me know. We'll answer your questions. We'll make sure you understand this process, right? And if you haven't done so, please like, subscribe, share this video with somebody who might need it. You might help them understand why they want to eat fat. They want to not eat carbohydrates, because the difference in which you get out of energy out of them is significant. Thank you very much.